One of the biggest mistakes in the clean energy conversation is assuming that all energy problems are the same problem. They are not. Energy challenges exist across different dimensions, and when those dimensions are collapsed into a single comparison, confusion follows. This is exactly what happens when batteries and hydrogen are discussed as if they were interchangeable. They are not. They operate on entirely different axes of the energy system. At the most fundamental level, batteries optimize energy and time. Hydrogen optimizes energy and scale. Once this distinction is understood, much of the noise surrounding energy storage debates disappears. Time is one of the most unforgiving constraints in modern power systems. Electricity must be balanced instantaneously. Supply and demand must match not eventually, but at every moment. As renewable energy penetration increases, this challenge becomes more severe. Solar and wind are variable by nature. Clouds move. Wind shifts. Demand fluctuates unpredictably. Batteries exist to solve this exact problem. Batteries respond in milliseconds. They absorb sudden surges of power and inject electricity back into the grid almost instantly. They smooth frequency deviations, stabilize voltage, and manage rapid fluctuations that would otherwise destabilize the system. In this role, batteries are not just useful, they are essential. No hydrogen system can replicate this level of responsiveness, and it should not try to. Hydrogen was never meant to solve millisecond-level grid control. Hydrogen enters the system where time-based solutions reach their limits. When energy needs to be stored not for seconds or hours, but for days, weeks, or even entire seasons, batteries quickly become impractical. Costs rise exponentially with duration. Material requirements explode. Physical footprints expand. At that point, scale becomes the dominant constraint, not response speed. Hydrogen is fundamentally a scale solution. It allows enormous quantities of energy to be stored in molecular form. That energy can be transported across long distances, stored for extended periods, and delivered to end users far removed from the point of generation. This is why hydrogen appears repeatedly in discussions about heavy industry, shipping, aviation, and seasonal energy storage. These sectors are not constrained by milliseconds. They are constrained by volume, endurance, and reliability. The failure to separate time optimization from scale optimization is why so many energy discussions go in circles. Batteries are criticized for being too expensive at long durations. Hydrogen is criticized for being inefficient at short durations. Both criticisms are correct and irrelevant at the same time. Each technology is being judged outside the domain it was designed to serve. Modern energy systems require both domains to be addressed simultaneously. Short-term volatility must be controlled, or grids collapse. Long-term imbalance must be absorbed, or renewable energy is wasted. Batteries and hydrogen are not competing answers to the same question. They are answers to different questions that exist within the same system. This distinction becomes especially important when looking at green hydrogen production itself. Electrolyzers do not operate in a vacuum. They are connected to real grids and real renewable assets. When power input fluctuates rapidly, electrolyzer performance suffers. Efficiency drops. Degradation accelerates. Operating life shortens. These effects are well known in industrial settings, yet they are often ignored in simplified hydrogen narratives. Batteries provide the time optimization layer that electrolyzers need. By buffering short-term fluctuations, batteries allow electrolyzers to see a smoother, more predictable power profile. This does not just improve technical performance, it improves economics. Electrolyzers that operate more consistently produce more hydrogen over their lifetime and do so at a lower cost per kilogram. Scale optimization enters the picture once hydrogen is produced. Hydrogen enables energy to be stored beyond the temporal limits of batteries. Excess renewable generation during periods of low demand can be converted into hydrogen and stored until it is needed days or months later. This is particularly important in regions with strong seasonal variations in renewable output. Batteries alone cannot economically bridge seasonal gaps. Hydrogen can. Curtailment is where the failure to integrate time and scale becomes most visible. As renewable capacity grows, more electricity is produced at times when it cannot be consumed. This energy is simply thrown away. Batteries capture some of it, but only within limited time windows. Hydrogen provides an outlet for absorbing large volumes of surplus energy without immediate time pressure. When batteries and hydrogen are combined, curtailment drops dramatically and overall system efficiency improves. These system-level effects have direct financial consequences. Projects are not financed based on theoretical efficiency. They are financed based on predictability, utilization, and risk. Assets that sit idle for large portions of the year destroy returns. Assets that operate smoothly and consistently attract capital. Hybrid systems that optimize both time and scale outperform single technology projects on these metrics. This is where many clean energy projects fail quietly. The technology works, the physics are sound, but the system is poorly designed. Timelines slip, costs creep upward. Revenue assumptions prove optimistic. These failures are rarely blamed on system design, but that is often the root cause. Designing hybrid systems that balance time and scale is not trivial. It requires coordination across engineering, grid integration, commercial contracts, and finance. Renewable assets, batteries, electrolyzers, grid connections, and offtake agreements must align not just technically, but temporally. Delays in one component cascade into others. Without disciplined planning, complexity becomes risk. This is why execution tools matter. Large-scale energy projects are not managed successfully with informal planning or disconnected spreadsheets. Professional developers rely on structured project planning platforms such as Microsoft Project to manage dependencies, critical paths, and milestone alignment. When multiple technologies are integrated into a single system, execution discipline becomes a competitive advantage. Understanding how to design these systems is equally important. Many professionals entering the hydrogen space come from adjacent industries and lack exposure to hybrid energy architectures. They understand individual components but struggle with system integration. This gap is where costly mistakes occur. H2Hub at h2hub.renewable.com was built specifically to address this gap. It focuses on real-world green hydrogen project development, emphasizing how time-based and scale-based technologies are integrated into bankable systems. The goal is not to promote hydrogen in isolation, but to teach how hydrogen fits within broader energy stacks that include batteries, renewables, and grid infrastructure. The misconception that batteries will eventually make hydrogen unnecessary stems from ignoring scale. Likewise, the belief that hydrogen can replace batteries ignores time. These misunderstandings persist because the discussion is often detached from operational reality. Engineers, grid operators, and developers who work with these systems understand that both layers are indispensable. As grids become more complex and decarbonization efforts move into heavy industry, the importance of this layered approach will only increase. Industrial users demand reliability measured in months and years, not minutes. Grids demand stability measured in milliseconds. No single technology satisfies both constraints. The future energy system will therefore not be defined by a single dominant storage solution. It will be defined by architectures that intelligently allocate roles. Batteries will continue to dominate short-duration control. Hydrogen will continue to dominate long-duration and industrial energy supply. The systems that succeed will be the ones that respect these boundaries and design around them. This is not a compromise position. It is an engineering necessity. The laws of physics, economics, and infrastructure impose limits that cannot be negotiated away by narratives or preferences. Systems that align with those limits thrive. Systems that ignore them struggle. This series is about making those limits visible and understandable. It is about replacing oversimplified debates with practical frameworks. Batteries optimize time. Hydrogen optimizes scale. Once this is understood, the energy transition stops looking like a battleground and starts looking like a design challenge. If you want to develop the skills to design, model, and execute hybrid energy systems that work in the real world, the tools and training at https://h2hub.renewable.com are built for that purpose. And if you are managing complex energy or infrastructure projects, The Microsoft project tools linked in the description are the same platforms used across large-scale developments worldwide. Clean energy will not succeed on ideology alone. It will succeed through systems thinking and disciplined execution.